Hey everybody, Tak is back with another surface phenomena video. This time, we're going to be conducting an adhesion experiment. The goal of this experiment is to determine the distance between the two acrylic plates in which water is adhering to the solid surfaces. As you can see from figure 1, which is from the surface phenomena textbook, we have two plates and there is going to be liquid between those two surfaces. And we have the equation shown right here on to the right, along with just showing a colored picture of how this experiment is going to be conducted. Keep in mind that the red arrow indicates a downward force, in which is going to be the weight applied to surface 2, which is going to break the adhesion force of the water tacked to surface 1 and surface 2. The materials used for this experiment are liquid water, a small cup, food coloring, in which I kind of mix it with magenta and teal. Item 2 is going to be tape. We also have acrylic, we have a disposable pipette, a digital caliper, a digital scale, paper clips and binder clips, an envelope which is going to be our container, and a snap clip. The setup will consist of two acrylic plates with liquid water adhering to the solid surfaces. Weight will be suspended underneath acrylic B. The weights consisted here will be the snap clip, binder clips, paper clips, and the envelope. The coins will be loaded into the envelope to help us determine the amount of mass in which the adhesion force will break. With the acrylic pieces used in this experiment, finding the surface area is critical. As I don't have any special equipment to cut the acrylic material nicely, my pieces were not the best. However, I was able to extract the dimensional profile of the two acrylic pieces since there are curvatures shown here. I did use a software to help extract the raw data points on my two photos to extract their dimensional profile. From referencing the horizontal and vertical distances in millimeters, plotting along the curvature helped develop the corresponding data points. This software did provide a CSV file of my extracted data points, and I was able to graph those values along with obtaining the area under the curve with the help of Excel. From the bottom left table, I did extract the area for both pieces. Since I'm only using acrylic B for my area, it would be wise to compare and contrast with acrylic A to ensure my surface area values were reasonable and validate if my technique worked or not. Here we assume gravity to be 9.81 meters per second squared, water is ambient temperature, and the liquid fully wets the two surfaces in which theta is equal to 0 degrees. I have also analyzed the mass for the coins, along with acrylic 2, the hooks, tape, and envelope as one whole system to help us analyze for the mass, which I'll show towards the end. Before moving on to the next slide, I do have the derivation shown here on to the right, along with the source that I found for the surface tension of water at ambient temperature. On to the experimental procedures, we would first have to fill up the cup of water with food coloring, and then add a drop of the liquid to acrylic piece number 2. Once you have the drop of liquid onto acrylic number 2, then you have to place it under acrylic number 1. Once the two surfaces settle, then you can start adding the coins into the envelope. On to the results, we are able to solve the equation to find h, which is the distance between the two surfaces with water adhering to both sides. With 5 pennies, 7 quarters, and 1 nickel placed into the envelope, we are able to add the overall coin mass, in which is shown right here, of 56.2 grams. And we also have the mass for the acrylic piece 2, hooks, tape, and envelope as one system, with a mass of 39 grams. Adding everything all together, we're able to convert from grams to kilograms, and the overall mass for what we have is 0.0952 kilograms. With the perfect assumption of perfect wetting, along with the liquid being ambient temperature, we do obtain the value of 0.44 millimeters. It seems about right since we're kind of going off of these assumptions, since it would be kind of difficult to detect the surface's distance with water in between from using my digital caliper. Last but not least, the conclusions and final thoughts of this experiment. So I felt like the loading technique could have been improved for this experiment since I was kind of inconsistent for how I placed in the coins itself. I should have added more tape to the acrylic piece number 2, as you did notice that it did slip off during the experimentation. There could be an assumption that my surface area could have been slightly off from the approximation. I also felt that assuming that theta equaling to 0 degrees isn't the best idea since there's going to be a contact angle between the liquid and solid surface. Another thing I can also consider is that the resolution on the digital scale could be pretty low, which I'm not able to get the exact mass for whatever I'm measuring, but it is what it is. Before I wrap it up, this experiment wasn't too much of a disaster, but I was able to get some results of what my H would be, along with just assuming these assumptions of perfect wetting, along with water being ambient temperature. Thanks for watching the video, guys. See you in the next one.